This presentation shows our achievements on magnetic colloidal dispersions in ionic liquids for thermoelectric liquid cells. The work is performed at Phoenix Laboratory, partner of the European project Magenta. Its aim is to develop thermoelectricity with liquids, whereas it is yet mostly used with solids. The idea is to recover wasted heat using two electrodes of different temperatures, and the liquid in between converts the difference of temperature into a difference of potential. Therefore, new complex liquids are needed, made of abundant and non-toxic materials. The idea is to associate ionic liquids and nanoparticles. The ionic liquids are new solvents, made only of ions, big asymmetric ones. They look like any solvent by eye, but they have numerous interesting properties. For example, a wide temperature range where they are liquid and stable, a low vapor pressure enabling uses under vacuum, significant electric conductivity, and others. The nanoparticles are iron oxide. Here, small rock-like nano-objects of 10 nanometers in size. Their specificity is a magnetic moment, so that each one is a nanomagnet. When their dispersions in liquid are stable, they have special properties under a magnetic field. For example, sticking on magnets, as you can see on this picture. If you mix both systems, you will finish with powder under a liquid in many cases, which you don't want for the project in thermoelectricity. You need a homogeneous liquid. So in a classical solvent, the nanoparticle-solvent interface has been widely studied and is known. This is not the case in ionic liquids. However, this region, the red one, controls the resulting dispersion state that you obtain, and it can be tuned. We illustrate the process to produce the samples with a short sequence on a small test sample. We begin with the dispersion in water, where the particles have been synthesized. They are charged, and the counterions are here the purple ones. The first step is to remove the charge from the particles in order to remove the initial ions so that they can be washed by several steps, removing the liquid that you see above the particles, however never drying them. After several of these washing steps, we can introduce a new charge on the particles and the desired species, here the blue counterions for example. Once the interface is tuned, the ionic liquid is added. You see the drops of the transparent liquid. After a stirring time, in this case, it appears that the particles moved from the aqueous phase at the top to the ionic liquid denser phase at the bottom, both liquids being immiscible in the present example. Whatever happens at this stage, the next step is to remove water by pumping. At the end, we recover the dry ionic liquid only, which is now the solvent. In this example, the liquid seems homogeneous by eye and follows the magnet. So it seems okay, but there are many questions. Thanks to a multi-scale analysis from the centimeter scale by eye to the nanometer scale by several techniques, we could demonstrate that samples stable on long times are obtained, several samples are stable at 200 degrees, several samples are stable under a magnetic field. At this stage, we thus have robust magnetic complex liquids. Among these liquids, some improve the power output of a thermocell, which is measured by other partners. We also have a toolbox of techniques and processes to find the best candidates and develop this family of liquid nanomaterials. This also opens future extensions. Magenta uses the magnetic and conductive properties of these liquids, however they also absorb light. Therefore, solar applications in energy can be envisaged, and other kinds of applications exploiting other properties, like magnetic deformation. Another possibility is to tune the properties. On the one hand, the liquid can be changed. There are thousands of combinations resulting in design properties of ionic liquids. On the other hand, changing the nature of the material, for example using other magnetic oxides or non-magnetic materials like titania, ceria, carbon particles, or nanotubes, can be of interest for nanofluids, catalysis, or other domains. Thank you for listening. You can find more information on the website or contact us by email.